Welcome to the channel. Today we're looking at a small GPU that I implemented in system Verilog. It's a minimal SIMD SIMD style compute unit. So think SIMD stands for single instruction multiple data, but except that we are broke and we don't have $1 billion budget. So the goal was to explore how a basic parallel processor handles things like thread blocks, memory access, and instruction flow, all while keeping the design simple enough to simulate quickly. So let me move myself over here. Um, so in this video, I will be teaching you how you can make your own GPU in Verilog. So we'll go to the architecture using these handwritten notes, using my handwritten notes, and then cover the key modules, and then finally, actually simulate this using a tool called cocoTB. So no miracles here. It's just a functional GPU. It's a toy GPU, I'd say, that can run all the matrix addition and multiplication for now, but it can grow into something if we keep working on it. Okay, so now, as you can see on my screen here for a while, I have the high-level architecture here. So if you zoom out a bit, so you can see that this entire unit is a GPU. Okay, so it consists of this thing called, at the top we have this thing called a device control register. Okay, then we have a dispatcher, and then a dispatcher controls all these compute cores. So, and then of course there, we haven't implemented caching yet, but caching is optional. You could always access it from memory, or you could build a cache so that this course don't need to reach out to the global memory every time it needs some frequently accessed data. And then, of course, to access the data, you have the program memory controller and the data memory controller. And finally, about the memory itself, we have the global memory, which just consists of our program memory and the data memory. Okay, so I'll quickly give you an example of the code, the kind of code that we want to run. So before we go into the code, let's look at the instruction set architecture. Okay, so I'm blocking the view here, so I'll move myself over here. Okay, so this instruction set architecture is very simple actually. We just have a no op, a branch operation, compare operation that sets the NZP register. NZP just stands for negative, 0, or positive, so that's it. Then we have all these arithmetic, so add, subtraction, multiplication, division. Okay, and then we have the memory ones, which are load and store. And then finally we have all these constant operation, like you want to give in store the immediate value in the register, you can do that. Or and then the best instruction, I'd say, return, because you're just done with this thing. So with all these instructions, let's go look at the kind of programs we're going to run. So give me a while. So here, let's say this is matrix addition, right? So the thing is, we have two 1x8 matrices, A and B. So A is filled with values 0 to 7. Let me zoom in a bit more. So B is filled with values 1 to 7, 0 to 7 as well. So now what we're going to do is, you can okay, so this is basically assembly code before we get into it. So this is known as assembly code, and it's kind of you can kind of get the idea of what's happening here already. You might be familiar with assembly code, I guess. So what we're going to do is we're going to start 3 registers, right? So the first register is R1, which stores the base address of matrix A. In this case, it's stored in memory location 0, so we give it the value 0. And then we have R2, which well, it's in location 8, and R3, which is our result, which we haven't specified here. That is going to go in memory address 16. So okay, let's look at the math happening here. So what we do is, you can think of this this stuff stored in R0, that is I. I is like the ith element in matrix A and B. So when we're adding two matrices, the equation turns out to be this one: Ci equals Ai time plus Bi, right? So all this code is telling us that we're going to calculate this index dynamically and split this across basically 8 threads, so that all of the 8 additions happen in parallel. And that's pretty much it. That's what's happening. So here we access what's in address A, the base address of A. So we go to the ith address, so base A plus I, and we get the stuff that's in the memory in that location. The same for B. Then we perform an addition on the registers, and then what we do is we store the. So we're back to this code here, and basically you can see now that we're gonna split this workload across 2 cores, and each core has 4 threads each. So that's what we're gonna do. So what we're gonna do is, we have 8 threads, right? And let's say we have 2 cores, and each core can handle 4 threads. So how many blocks? We're gonna group these things into so-called blocks. Okay, so we're gonna group all of the instructions, 8 of these, into something called blocks. We're gonna group these threads into blocks. So right now, each core, we have 2 cores, and each core can process 4 threads at once. So if we have 2 cores, we can process 8 threads at once. Simple, right? So what we do is we split the 8 threads into 2 blocks of 4 each, and then we send the first 4 to the first core to compute, and the second 4 to the second core to compute, and then we'll be done with all of the 8 additions parallelly. Yep, that's the basic idea. So onto the core structure of the GPU. Note that we have only 2 cores here. I just kept 4 here because, well, let's not get into that. Okay, so here we have the device control register, which basically just stores the number of threads, to be honest. That's it. That's all it does. And then it sends that information to this dispatcher. Okay, so the dispatcher is responsible for the creation of blocks and the distribution of blocks. So know that there is a specific rule we follow when giving blocks to cores, and that is you can give only 1 block to a core at a time. And each block has a certain fixed number of cores threads that it can group. So there's like a maximum limit of number of threads that can be in a block, and that is the block dimension or the number of threads in a block. So in our case, it is 4. So each block can handle 4 threads, and that's what is basically this physical hardware here. So the block dimension actually depends on your the implementation of your code. Okay, so now that we know that the dispatcher gives blocks to the cores, it has to be done in a synchronous manner. So we have to wait for the current block to be processed, and only then we can send in the next block to a specific core. Okay, now the core itself is built of all of these units. So the scheduler gets all of the info from the dispatcher. Okay, so let's go into my notes actually here. I think this is where my notes will be useful for you guys. So give me a second. Let me pull up my notes. Okay, so here are my notes. Don't mind, they can be a little messy, but I'm hoping that they can point across. So, okay, so here, a scheduler is what manages an entire compute core. So it kind of interacts with the memory, it interacts with the fetcher, the instruction fetcher interacts with the program counter, and it also interacts with the decoder so that it can let the dispatcher know when code is done executing. So if you go here, so you obviously need to know when a core is done processing, right? And that is done by the scheduler. So the scheduler kind of tells the state of the core. So is it free, is it busy, etc. So it can each core has its own scheduler, and the dispatcher interacts with the scheduler of all the cores. So that's hence the name scheduler. So it can schedule when blocks are assigned to it. Okay, back to my notes. So as we see, it interacts with the decoder and also outputs the core done signal, which is used by the dispatcher. Yep, that's pretty much all it is, and we'll look into the code later, but let's get the general idea first. Okay, so now once a block has been scheduled for a core, what you do is you fetch the instruction. So the fetcher accesses the global memory, and in this case, it accesses the program memory in global memory because it fetches the instruction from there and then gets it to over here. Okay, and then what happens is it goes to the decoder. So what the decoder does is set control signals and understand the instructions. So it tells the ALU what operation is going to happen. So, and it tells, is it addition, is it division, do I need to access memory, so on. And all of those control signals are sent to all of these thread processing units here. So let me pull up a picture of the thread processing unit. So here is what thread execution unit looks like. We have the ALU, the LSU, the register file, the PC, and the MUX, and many MUXes, which are driven by the control signals from the decoder. So yep. So now the next thing we have left is only analyzing the thread execution unit. So the thread execution unit consists of a register file. So let's walk through a simple example here. Okay, so let's walk through an example code here actually. Okay, so this might look stressful, I don't know if it does, but okay, let's go through and understand what happens in a single thread execution unit. So I have our assembly code on the right and our thread architecture on the left over here. So what we're gonna see is here, this is our assembly code first here. So here, the first instruction we're gonna calculate is basically, we're gonna calculate the address of the mattress I that we want to add, so that we can get Ci equals Ai plus Bn. So what we do first is, well, to get the current address, it's actually kind of simple. So what you do is you get this block index and block dimension that basically gives you the ID, the starting thread of the block. So in our case, we have 2 blocks. That's block 0 and block 1. Now, block 0 has threads 0 through 3, and block 1 takes care of threads from 4 to 7. So, well, what do you do? Thread index is basically a number between 0 and number of threads minus 1. So, in our case, number of threads is equal to 4. So, to get I, what we're going to do is we're going to multiply block index into block dimension. So here, since we have 8 threads, we're going to have 2 blocks. So let's say the first block comes, and we have 0 here, and we have the block dimension is 4. That's fixed because the number of threads is 4, and our design says so that it's 4. And we're going to add the thread index that's going to come. So thread index is going to be 0 initially. So you're going to see that since we have 4 cores, so let's go back to the core here. Since we have 4 cores, yeah, so this part is going to get thread index 0, this part is going to get thread index 1, this part is going to get 2, this part is going to get 3, and that's all there is to it. That's simple. So let's assume we're on the first core here, so that's it's always going to receive thread index 0, so it's going to be 0. So this unit is responsible for adding A0 and B0, and this one is going to be responsible for adding A1, B1, this one for A2, B2, and this one for A3 and C3. And similarly, the other core is going to add A4, B4 to A7, B7 parallelly. Okay, so now that we gotten that out of the way, we are storing this particular index in 0. So to access the ith location, we of course need to add the base address of the array or matrix to with I to get the correct memory location. So in this case, we know that the base address for A is actually 0 because it's in the 0th location in memory, and the base address for B is 8 because it's in the 8th location in the memory, and 16 is where we're going to store this because the last location of B is actually 15. So assume that there's a 16th position here, and that's where the result of addition is going to be stored. So what we're going to do is first calculate these addresses. So we're going to store the address of A in this register called R4. So we're going to add R1 and R0, which is base A plus I, and we're going to load this specific value from R4 again into the same register itself because we don't need the address of AI anymore. We're going to do the same thing for B over here. And the only change is that we're going to store the value of BI in R5, and the base address of the address of matrix BI is in this R2. So finally, we're going to add the result in another register R6, right? And we're going to calculate the address to which we're going to store this to in the memory, which is base address of C plus I, and let's call that in R7. And we're going to store the contents of R6 in the memory address of R7. So that's storing in global memory, and then we're going to return. Wait, that was not hard, right? So let's see how this happens in hardware. So let's say we receive a multiplication instruction. So the multiplication instruction says to multiply block index and block dimension and store that in R0. So what happens when you get a multiplication instruction? Well, for the first thing, since you already have the values over here, right, you're going to multiply them. So you're going to take in the inputs RS and RT from the registers. Okay, so there are special registers reserved for block index, block dimension, and thread index. They have their special registers. So we're going to so you can assume them as some special registers. Let's say R-0, R-1, and R-2. This could correspond to block index. This could correspond to block dimension, which is 4, and this could correspond to thread index. And all this is actually passed down by the scheduler, by the dispatcher to the scheduler of the core. So that's how we access these values. So we're going to access the registers address of block index and block dimension. That's going to be our RS and RT for the operation. And we're going to set register write enable to 1 so that we can write back to the destination register, which is R0. So we're going to take this here, and the arithmetic mux is going to say that, okay, you're going to be in the multiplication mode. So we're going to issue this control signal. This is just an example, but this is what the decoder is going to give to the arithmetic unit. And then the arithmetic unit is going to multiply these two values, and it's going to go over here. It's going to update the program counter as well so that we can move on to the next instruction. And then it's also going to in this case, the decoder is going to say that, okay, we need to choose the ALU's output here to write back into the memory. So this mux basically chooses what is written back into the register file. So in this case, we need to store the result of the multiplication back into R0, where the R0 address is specified over here, and the data that goes into R0 is passes through here. So that's all there is to multiplication. As you can see, the flow is very similar for addition, except for the fact that you're going to have a different control signal over here, and that's about it. So constants are just storing, so you can just get the immediate over here, and that's gonna just write back to the memory. That's all that's gonna happen for the constant instruction. Now the LDR instruction. So if we go back to the ISA over here, so let's go to the ISA over here. Okay, now we are here in the ISA, and let's take a look here. So the LDR instruction accesses what is in the address at RS and stores it in RD. So in this case, RS is R5 over here, and RD is R5, RS is R5. So we're going to access what's in memory location that's stored in R5, and we're going to put it back in R5. And the control path looks like this. So we're going to pass in RS here, okay, and we're going to pass in RD here. So RS is taken over here, and this goes into the LSU unit, okay, which accesses the global memory and gets what is in global of RS is what comes out here. And the mux here, the decoder chooses the control signal output LSU out this time, and that's what gets written back to the memory. And the RD address is same as the RS address, so the contents of R5 is written with what's in the memory of global of R5. Yep, and that is the LDR instruction. There are a few more add instructions which store the result, and then finally there's a store instruction, which is also pretty similar. So if you go back to the IC, the store instruction basically takes what is in RS, okay? So it takes whatever is in RT and puts it in the address at RS. So in this case, RT is actually R6, so R6, and R7 is actually RS. So we're going to store the value of addition, which is R6, into the memory location at R7 because that's the address of CI. So the control path is going to be similar for this. We're going to take the value of RT, whatever is in RT. Let me just clear this up. Okay, so we're going to take whatever is in RT, and then it's going to go to the load store unit, and we're going to say that we're enabling memwrite and disabling memread. Okay, I forgot to mention that earlier for the load instruction. In the load case, memread is 1 and memwrite is 0. That's pretty much the same thing. So now we're going to take the value of RT, and what we're going to do is we're going to take the value of this one here as well. So we have RS as well. So here RT is R6 and RS is R7 and R6. So what we're going to do is we're going to take this value and go to the global memory of R7, and then we're going to store R6 in that. That's what is going to happen here, and we have no LSU out from this because we're just writing to memory. We just need confirmation from the memory that it's written, and then we are good to go on to the next instruction. And we see that the final instruction is a return, which puts the score, which kind of resets all the control signals in the score and sets it back to the initial case or the 0 case. So basically we pass no operation to the score. Is that what happens? So I hope now you understood what this entire GPU thing is about and how it does stuff in parallel. We'll be jumping on into the codes of this pretty soon, so you can skip that part if you want. But if you want to understand how Verilog works and want to know how I did it, how I analyze this repository, stick around, or you can skip to the part where we try to simulate the GPU. Okay, so now it's time to actually get this GPU running by Verilog simulation and verify that our output is actually correct, mathematically correct, through test benches. So for this, we will be using cocoTB in Python. Now note that for this specific project, there is an issue, a build issue, where you need to use a specific version of cocoTB. So if you have cocoTB already installed, then install it first, and then install this specific version of cocoTB. Okay, now once this version is installed, so okay, you need build tools. So go ahead and download build tools if you don't have build tools. Okay, so now we're actually going to check if our GPU works through Verilog simulation. So what I have opened here is a new terminal window, and I'm using Python from the official website, not from the Microsoft Store, because there are certain issues with Python from Microsoft Store. Now, before you install the specific version of cocoTB, I'd recommend that you have Visual Studio build tools installed, and let me show you what I have installed real quick. So what I mean by build tools are the C++ one specifically, and only these suffice. So I already have the MSVC and Windows 11 SDK installed, so that's what you need to install for this. Anyway, if the installation does fail for you, it will show you the prompt that you have to install this. So just install it and keep it ready. Now, there's an issue with the official GitHub repository, and that is that the Makefile only works on Linux systems. So if you want to build and test this project out on a Windows PC, you'll have to use your own script. But luckily, I have made a script for you guys so that you can use it with the same arguments. So we're going to do test underscore matat, and the script name is build, and it's a PowerShell script, so you run it in PowerShell. Okay, just run it, and okay, so you can see that the test has successfully passed, and it actually took this much time. And there we go, our GPU essentially works. Now, if you want to look at how it has been executed, we can go into the test and then into the logs folder. We can go into the latest logs over here. And there we go. These are the logs for today, which you can see every cycle, what happened in core 0, what happened in thread 0, thread 1, thread 2, so on. So stay tuned for a live stream where I'll be explaining the code behind this because it could get a little long. So that's why I'm planning to do it as a stream. But do let me know if you want to do it through a video, which will be short and compressed, or do you want it in a live stream? Okay, that's it for now. We have successfully built our GPU that performed, added 2 matrices in a single, let's say it executed 8 threads in parallel. That's what we did. And you could, of course, make the code. The code is modular, so you could experiment with more threads, and maybe let's try implementing this on FPGA next time through the AMD Vivado software. So stay tuned for that. We'll be looking into how this can run on an FPGA, and once it's on an FPGA, we can do all sorts of crazy things like attach a display to it, run some graphics, and etc. All right, thank you for listening, and this is how we start building a GPU in Verilog. So it may be simple for now. Stay tuned, we'll keep improving it.